My name is Gamayunov. I'm a senior researcher of the Lomonosov Moscow State University, Russia. And my co-speaker Svetlana is my PhD student, and we're going to present our work on shellcode detection. Part of the presentation will be mine, and the rest of the presentation, the most valuable part, will be presented by Svetlana. I will try to speak a little bit about motivation of our work and state of the art, and the rest of the presentation will be about our proposed approach and its implementation and the evaluation results and everything and so on. And this will be done by Svetlana. I hope she will not leave me alone here. Okay. The first question which people tend to ask when they hear about shellcode detection in 2013 is, why should we care about it? It's about 2 decades or maybe more when people are trying to, well, people actually do memory corruption, overflows and exploitation, and maybe this problem should have been solved already. Yeah, it's even there are even jokes on the internet about knob sleds, which you may find in comics, and there are a lot of cons. Why should anyone care about shellcode detection? It seems like old. We have around here Web 2.0 and clouds and scaling the clouds and everything, and some will say that this is a little bit strange. And if we look at some statistics, for example, Microsoft's this statistics is about a year and a half in age, and it states that the #1 reason for malware propagation, for example, today is user inawareness. It's when people just don't know that you shouldn't run those executables that come to us as attachments, for example. And this reason is about, well, 60% maybe of malware installations. And the next one is, I don't remember which exactly. And the third one is memory corruptions exploited remotely, and they possess only less than 1% of all cases where malware installed on the end user systems. And it may seem that endpoint security products work well. Well, we have a lot of antivirus software which may be deployed on any kind of modern operating system. I mean, Microsoft products is ahead, but we have Linux flavor antiviruses for mail server setups and so on. So we have a bunch of endpoint security products which are known to users, and users know how to use it, and that's why should we care? But, well, the last half of a year helped me a lot, me personally a lot in this talk, because we had several sequential cases of 0 days in Java. And before last spring, yeah, we can remember remotely exploitable vulnerability in Microsoft remote desktop service, which didn't actually it wasn't necessary to have any any identity in the network which to successfully run this exploit and get the privilege escalation remotely. And if we imagine ourselves as people who are trying to mitigate such risks, what can we actually do? Because antiviruses and endpoint security products, they act proactively. They actually do act proactively, but in very limited scale. And our own, for example, our own penetration testing experience shows that it's quite often easy to shut down antivirus service while exploiting the remotely exploitable vulnerability like this, and that's all. And it maybe it would be interesting for me personally as a user of some detector to distinguish from, for example, attacks which are detected by Snort or some other intrusion detection systems, or when they give false positives for executives download, something like that, to distinguish from cases when script kiddies take Metaspoit Framework and try to find vulnerabilities in my network. Of course, many of us heard about advanced persistence threats and targeted attacks of critical infrastructure. We think that this may be also a kind of market for tools that allow, to some extent, detection of unknown malware, unknown shellcode exploits. A good example. We have a CTF team in Moscow State University, and I used to play with my students also in CTF, and it's kind of very a situation which can be tense and filling when you're defending your setup, and it's kind of in the middle of the game. You see that your vulnerable services are getting to show strange behavior. It's like someone found already the vulnerability and exploiting and getting the flags. But you cannot see what exactly is happening because it's a lot of traffic. The traffic is full of, you can say that any session from other team is maybe malicious. You cannot analyze it fast enough to understand what's happening to the service. So the software which could allow to automatically grab actual shellcodes from the network traffic would be valuable for us as a team to play in the games. And also we have vision for the future use of shellcode detection methods, not signature-based, in the mobile internet, mobile clients security. Because if we look at what is happening right now in the mobile platform security, we can see that the situation is somewhat similar to what we saw 15 years ago in fixed point security systems, when the primary risk which was analyzed by the administrators or users, was how to protect the information on my PC or on my server. And later, much later, in the beginning of the 2000 of the previous decade, cyber criminals found ways to earn money on the mass exploitation of personal computers without stealing some critical user information. I mean, building botnets for denial of service attacks, for mass stealing of credit card information, and so on. And today, mobile platforms, they are already outnumber the number of fixed computers on the internet about 4 degrees magnitude. I mean, it's about over 1 billion devices connected to the internet, which are presented by Android, iOS platforms, and so on. And only about 200 million fixed devices. And they are maybe not yet interesting for cyber criminals in terms of building some large volume botnets, because they don't have constant internet connection, which may allow to use them as the ordinary botnets are used now. And the only thing that may be how malware may allow an attacker to earn money on the vulnerable machine is to steal personal data, for example, banking data. Yes, and if the situation is similar to what was 15 years ago in the fixed market, we can imagine that it will develop in the similar way in the future when cyber criminals, when for example we have full coverage of broadband wireless connections like LTE and so on, and there will be ways to monetize this remote exploitation in many ways, and then it will be much more interesting to find server-side, client-side vulnerabilities and exploit them remotely. So this is the motivation for our work. What we are trying to do, we're trying to combine existing shellcode detection methods which were developed in recent 10 or 15 years by researchers and industry, and to allow to build something that may be useful in right now and in the future. I mean, to do so that solution which we're developing right now will be extendable to allow different architecture platforms, different operating system flavors, and so on. I will talk a little bit about existing methods for shellcode detection. They may be split generally in 3 major groups or types of analysis. Shellcode basically is a program, computer programs, which is limited in space. I mean, it's not always vulnerability, remotely exploitable vulnerability, and not always allow an attacker to write a lot of data into the address space. And there are, since shellcode is a program, it may be analyzed as a program. And there are some differences in how shellcode looks like and how, for example, virus or ordinary normal program like. And people try to detect this specific type of programs in three ways. There are static analysis methods, there are dynamic methods, and hybrid combinations of both. Static analysis methods treat the data which they are analyzed as a source code of the program, for example, in machine codes. This means that for analysis we do not need nothing but the source code. We do not need to run the program to analyze its behavior. Dynamic methods run the program in order to detect what it will actually do. In the field of shellcode detection, we may meet signature matching, as it's quite ordinary for antivirus and IDS systems. We may meet such methods like control flow graph or instruction flow graph analysis. There were specific methods aiming at knob sled detection, for example. The knob sled is part of the shellcode which contains only instructions which lead the execution down to the actual portion of shellcode which do this stuff which was intended for it. Dynamic methods all require emulation in some way. Emulation of virtual or execution in virtual environment, sandboxes and so on. They differ theoretically. They differ in code coverage, for example, because static analysis theoretically may allow you to analyze all the branches of code execution. But when we try to analyze shellcode without knowing the actual memory state of the machine which is being attacked, it's not always possible to find out data which is necessary for static analysis. The values of addresses which will be written or read from the memory and so on. Dynamic analysis is more and static analysis very badly behaves when the program is encrypted or packed, for example, and then it self-decrypts on the endpoint. Dynamic analysis allows to avoid these kind of problems and detect, unpack and analyze unpacked code. When we finished analyzing existing research, we found out that there were tools available on the internet also, like libemo emulator with some kind of shellcode detection features in it. There was libsizzle by George Wicherski, for example, which implemented hybrid kind of shellcode detection with cat PC code detection and emulation. Further, and there was a bunch of research work which we had to implement for ourselves because the code was not available on the internet, and then we analyzed these implementations and found out that it's not a surprise. Methods with low computation complexity had high false positives rates, and vice versa, methods which were good and accurate in detection, tested, for example, on recent Metaspoit, they showed very high computation complexity. What can we do as a user who wants to build a system from it to analyze traffic. If we want to defend mobile platform, we cannot run these heavy methods on the endpoint because it consumes battery and so on and so on. And we cannot actually run them on the network appliance because if we go to exact numbers of computational complexity, it turns out that, for example, that on some types of the data, the libemo or libsizzle processes about 200 kilobytes per second on the modern server. And what can you do actually with such kind of methods? But we tried, thought, and an idea came to our mind that maybe if we combine these methods in such a way that the fastest methods, the least complex methods will come earlier. And we will be able to make the coverage for different types of shellcode on the higher levels of this analyzing framework. And we will make so that the most accurate and heavy methods will be executed on the last stage. We will be able to cut the normal data on the earliest stage, and therefore we will run to the execution of the most heavy methods at the end, and thus reduce the complexity of the method. Svetlana, I'm giving you.
First of all, I've briefly described objects on which we are working on. Next, I describe architecture and details of implementation of our prototype, and also show the evaluation and some funny demo, maybe not funny, I don't know. In contrast to viruses, which are rich with features, with some characteristics, shellcode usually have strict schema. So, for example, here we have little example of shellcodes which exploits buffer overflow vulnerability. And in such case, shellcode should have at least return address zone, because we are aimed to override return address zone of our stack with the same value that leads the controller flow somewhere inside our shellcode. So as attacker may not be aware about some environment of vulnerable machine, so shellcodes usually have some kinds of activator. So it could be an obfuscated, it could be some kind of get PC code. An obfuscated, as it was mentioned before by my co-speaker, is the set of instructions which typically do nothing but increasing program counter. But in real life, we have pretty complex obfuscated which can do some arithmetical operation, do something on register, and so on. The only requirements it's not to affect control flow of malicious payload, of payload. So what attacker can also do? So usually they want to evade simple signature-based detectors. So that's why shellcodes usually have some decryptor routine in their schema, and also a payload. Here is some example. It's synthetic example generated by Metaspoit Framework. We have first block of instruction. It's an obfuscated. After that, we have decryptor routine and also encrypted payload, which will be changed during decrypt execution. Again, we have really impressive background on shellcode detection area. We have a bunch of algorithms which are characterized of at least four issues. It's execution time, it's false positive rate, it's false negatives rate. And also, let's imagine that we have different classes of shellcode. So we also can compare our algorithms with the feature how well and how many shellcode classes they are able to detect. So, and given all that stuff, why don't we try to construct some optimal classifier which will be optimal in terms of execution time, which will be optimal in terms of false positive rate. And we are also interested in detecting everything we can possibly detect. So such optimal classifier, such optimal solution should also provide complete class coverage. So during our analysis, we analyzed several research papers describing shellcode detection algorithms, several research papers describing how to exploit memory corruption vulnerabilities and so on. So what we've noticed, we have typically we have for several shellcodes we have some features. They can be static, they can be dynamic. So static features is features that which presence can be detected only by static analysis. Dynamic features can be detected by dynamic analysis only. So here is some examples of static features. Of course, the list could be much, much bigger. We have two types of features. It's generic and specific. As it was mentioned before, shellcode, it's a program. So generic features typically relies on the fact that shellcode is a program. So it was some research papers describing that if some piece of data disassembled is into instruction of some certain number of in the chain of some certain number of instruction, it should have it could possibly do something significant. So if we have less number of instruction, we could do nothing with them. It's just random instruction. So in their work, it was 14 instruction. So we could use such heuristic. We also can look at a number of hash call patterns, as well limited by the size of buffer. We have limitation on size and so on. Specific features usually relies on the presence of knobslet, presence of decryptor routine, typical for non-ISLR systems, and so on. Well, here's an example of dynamic features. We also have generic one. We also have specific one. It could be boring. Okay, so what do we have now? We have some set of features, and we want to split overall shellcode space into some maybe particularly overlapping classes. We have requirements that each class should be identified by a unique set of shellcode features. So they could be overlapping, and thus every feature can be reflected to several classes simultaneously. I'm sorry. Let's consider a simple example. Let's consider classes of multi-byte NOP equivalents, shellcodes. Again, as a program, we have some set of common features that it should disassemble as into a chain of relevant size. It shouldn't exceed size limitation. So as it multi-byte NOP equivalent shellcodes, we should have multi-byte instructions, surprisingly. And we also have requirements that we need such shellcodes to be correct disassembled from each and every byte of set. Because if we put our control flow to the wrong byte of set, we should be certain that we will reach malicious payload correctly. Well, depending on those features, we could present some set of shellcode classes. They could be grouped on some meta classes like activator-based classes, payload-based classes, return address-based classes, decryptor-based classes, and so on. Here is some example. Again, we could have classes of shellcodes which contains only shellcodes with x90 NOP-SLED. NOP-SLED could be more smart, more difficult detectable. So we could have classes of shellcodes which contains 1 byte NOP equivalence length, multi-byte NOP equivalence length, and so on. It could also be a trampolite sled which consists of jump instruction. So if we put our control flow somewhere in such NOP sled, we are sure that we will reach malicious payload in one single step. But unfortunately, it's such shellcodes can be detected by simple signature-based detectors very easy. So sometimes malicious guys do some obfuscation on such sled, and so on. Well, here's example of payload-based classes. So we could have plain unobfuscated shellcodes, shellcodes with different obfuscation. The first 1, 2, 3, 4, 5 bullets stands for polymorphic obfuscation of shellcodes. It's interesting also to consider metamorphic shellcodes, which provides two levels of obfuscation. While in polymorphic shellcodes we have a strict kernel of a program, and we do some obfuscation on that strict kernel. In metamorphic, we first of all we change the kernel of the program, and after that we can apply some polymorphic modification. So we have two levels of obfuscation. Again, here is examples of decryptor-based and return address-based classes. So they can be unpacking, self-unpacking, self-ciphered, non-self-contained, which are trying to execute malicious payload from different memory locations, and also return address zone-based classes. So it was object on which we are working. Here's some information about our prototype. Sorry. Okay. When we looked on existing shellcode detection algorithms, we've noticed that complex algorithms usually have pretty difficult heuristic inside of it and pretty difficult
typical routines maybe.
They have really pretty difficult heuristic, and they communicate with each other in complicated way. First of all, we tried to take several existing shellcode detection algorithms and to try to decompile and decomposite them into simple heuristics of which they are trying to detect during their analysis. Now we have. Unfortunately, we can't implement everything we found, so we have several algorithms that implemented and decomposited. So here we have some set of detectors of such heuristics of features. Moreover, we implemented simple detectors of features that I explained in the several previous slides. Well, we have detectors. Moreover, we noticed that during their analysis, all existing algorithms using common steps, like they all need to disassemble byte flow. Several of them need to reconstruct control flow graph from the disassembled byte flow, or instruction flow graph, or something else. So it seems reasonable for us to implement our tool as shellcode detection library as a part of our tool in such a way that is shown on the current slide. Well, okay, now we have shellcode detection library with the set of elementary classifiers. We formulating the task of detection shellcode formulating the task of construction hybrid shellcode detector that will provide complete class coverage that will be optimal in terms of false positive rate, false negatives rate, and execution time, in such a way that we're trying to construct a directed graph and the set of vertices represented by elementary classifiers, arcs represented by data flow between elementary classifiers. Well, such graph should have several levels. Each level represented by different elementary classifiers which detect different shellcode classes. Well, and two levels can be connected on a very specific way. For example, let's consider one elementary classifiers which are able to detect knob slots presence in the byte flow, and consider elementary classifier which are able to detect the presence of getPC code. How can we compare them? There's no way to do it. It doesn't seem reasonable at all. So we can connect only those classifiers which are able to detect overlapping classes of shellcodes. So the other idea was how can we try to optimize execution time of our detector? Well, idea was the following. Let's consider we have some elementary classifier. If we pass malicious sample through it, elementary classifier pass that malicious sample to the other classifiers to double check it. But if we have a legitimate flow and some elementary classifier concludes that flow is legitimate, we are not passing it through elementary classifier, such we are able to reduce legitimate flow as fast as possible. And thus another significant idea was to put less complicated classifiers on the top of topology, so we can reduce legitimate flow on the early stage of execution of the tool. Well, how are we building such classifier? We are given the entire set of elementary classifier. On every step, we choosing some combination of elementary classifiers from it, and we're saying that it will be the next level of our hybrid classifier. The next step, we're trying to link different lawyers, a new lawyer with other graph, and we removing the new classifiers from the new level from entire set, and repeat that step so many times before we have, while we have some elementary classifier from which we can construct the next lawyer. What? Levels, I'm sorry. So how can we select classifiers for the next level? Well, we have entire set of elementary classifiers. They're able to detect some subset of shellcode classes. We constructing all possible combinations of elementary classifier which are able to detect such a subset of shellcode classes. And after that, we're selecting the most optimal combination, which are optimal in terms of false positive rate and time complexity. Well, as we have at least two significant goals in our work. We wanted to detect every classes that we can possibly detect. We wanted to minimize false positive rates. So it seems very native that proposed linear topology can solve all our problems. In such topology, we execute in every elementary classifier after another, but the only requirement that we are not able to reduce legitimate flow. So every elementary classifier double-checking the output of previous classifier. And after that decision-making model analyzes all output from all classifiers and deciding that sample is legitimate or sample is malicious. Unfortunately, it's slow. But that's why it seems reasonable for us to have such linear topology as baseline in our evaluation. Here's a slide with boring numbers. While you're looking at those boring numbers, I try to explain datasets. We compared our our hybrid topology with linear topology on 4 different datasets. It was exploits generated by Metaspoit Framework. It was something about 2,000 samples. They were polymorphic, they were encrypted, and so on. We tried to do everything we can do. It also was data set of benign binaries. It was Windows PE and Linux ELFs. It was random data, and it also was multimedia data set. It can be strange, but during our work, we've noticed that some existing shellcode detection algorithms have failed to recognize part of multimedia to be legitimate. So they have really huge false positive rate. So it seems interesting for us how such approach can behave on multimedia also. Well, here's maybe a less boring visualization of boring numbers. Blue line stands for linear topology. Which color is it? Brown line stands for our hybrid topology. And the very first plot explains exploit dataset. As we can see, the difference on exploits dataset is not really significant. In ideal world, if every classifier if every classifier has zero false negative rate, so we should have the picture when we have similar lines on that plot. But unfortunately, sometimes classifiers failed to recognize shellcode. So that's why we were worried a bit how well our tool will work in terms of false negatives rate. But boring numbers shows us that it's still okay because of other elementary classifiers. So, and moreover, we have a little profit in time complexity, and we have much bigger profit on legitimate data set, and the biggest profit on the multimedia. At the multimedia data set, hybrid topology boosts linear topology up to 45 times. So here's a couple of use cases for the tool. It can be implemented as part of some IDS or IPS systems. In a way, like it shows on the current slide. So if hybrid detector concludes that some packet has malicious payload, we can simply drop it. So that's why we can possibly use it for detection of unknown 0 days. And also its experience of CTF participation, when we can try to get information from other team to monitor what's going on in our game network. Now I have a little demonstration how it works. Okay, the tool is open source. It's available on GitOris repository. Here demonstrating how to build it, use it from scratch. How fancy CMake? Fancy make.
Now in colors.
Its use case, how we can use such tool on detecting something in the network level. We can detect, as we can see, okay, there was plain shellcodes contained nopslets and so on. And here example, how can we detect something in files. We used malicious files generated by Metaspoit Framework. We used different models of Metaspoit. So we should see different classes of detected shellcodes. Here we have plain shellcode and nop shellcode. Still plain. Also shellcodes which contains some decryptor. So, here we go. Our tool named Morphos could be found on GitOris repository. Here's some information about me and my co-speaker. Such email addresses.
The URL is a little bit unreadable, yeah? Okay, I'll try to do this. If no. Okay. Oh. No. Oh, here. Still no.
Just click the mouse there and the pop-up will show the link.
Exploited.
Wow, too soon. No fate.
Okay. Well, the things which we can add that this implementation was made for Intel architecture 32 bits only, but we're currently trying to extend to ARM thumb architecture and 64-bit Intel architecture. If you have any questions, please feel free to ask them right now or maybe afterwards. Thank you. Yeah? So there is a question.
About false positive.
The false positives here in the slides.
So it's close to zero.
Close to zero.
Yeah.
The comparison was between linear topology when we were running every detector one afterwards, and comparing to this linear topology, it's almost the same. So we are gaining about 40 times without reducing accuracy much.